Okay, so let us begin. So, in today's class, we will talk about event-driven architecture, which is like last module of your course. So, in this particular module, you can expect some theory questions about whatever we'll discuss today. In the rest of the modules, you can expect some applicative kind of questions. So, why are we talking about event-driven architecture? Because you've already seen OpenMP, which is a shared memory model. We've seen MPI, which is a distributed memory model. We've seen CUDA, where we get massive parallelism using GPUs. So, after discussing all these different programming paradigms, why are we talking about event-driven architecture now? So, the short answer would be that event-driven processing is the backbone of almost every modern distributed system. And why? The first reason could be is concurrency, where event-driven architectures are designed to handle massive concurrency. And how? It is by instead of you blocking threads or creating one thread per request, which is very difficult to scale, event-driven systems are designed so that they react to events as the events arrive. So this makes it possible for event-driven system to support millions of concurrent events, which the traditional programming models were struggling. The second reason for learning event-driven architecture is it is executed in parallel. It is either executed like a stage or a function, and it is done in parallel. This parallelism that you get through event-driven architectures happens at multiple levels. Within a single machine, across multiple CPU cores, across multiple machines or cluster nodes, and even cloud environments, where across entire regions, you execute your requests in a event-driven processing. Hence, the event-driven processing naturally aligns with the goals of parallel computing. The third reason is distributed coordination. In a distributed system, we expect that the all the components are work together and try to work in such a way that they do not block each other, right? So here in event distributed system, we have something known as event queues, and they do exactly that. They separate the problem like uh, a producer and consumer and give us what we need. That is the with if based on how much is the request or how many requests are there, or you can call it load is there, it either expands the system or it will contract the system. Also, it takes care of fault tolerance, where events can be retired or it can they can be redirected. Also, it supports asynchronous communication, where this because of asynchronous communication, what happens is this reduces blocking. That is, we have scalable microservices within which different parts evolve independently. The fourth reason is we need this event-driven system because in real world, if you look at the systems which are widely used today, like uh, AWS Lambda, Google Cloud Data Flow, Kubernetes, right? Some of you all use it. They all share the same need. That is, they all are event-driven. They are asynchronous, pipeline-oriented, and they are mostly queue-based. So hence, to we must learn about what are event-driven architectures, because they are relevant from uh, this course perspective, because they prepare you to understand how cloud and distributed frameworks work. The last reason I would say that why you need to know about is because we learned about distributed programming through MPI and all, but we did not talk about what happens when distributed systems face unpredictable workloads, which is in most cases, right? We cannot predict what will be the workload. So if you want to build a reliable system, we have to understand what happens if there is a lot of workload. So, like, what are the what is the concept of a saturation point? What is peg pressure? What is fairness? You know, or what is how you, or how you guarantee the execution of systems. These are essential engineering tools which help you and to understand how to prevent failures, bottlenecks, or any kind of unknown or uh, unpredictable workloads. So let so event driven architectures is an important topic, and it's a nice way to wrap up this course, because it is the center of all the parallel and distributed computing today that we actually use in real life scenarios. If you understand how this model works, you will be able to appreciate how the modern cloud systems operate at these scales that we currently use. So you can call event driven architectures to be something like a task level parallelism. I hope you all remember we talked about data parallelism and task parallelism in the initial slides. So event driven can be put in the category of task level parallelism, whereas whatever we learned earlier, like MPI, OpenMPI, CUDA, was mostly about data parallelism or computation parallelism. So uh, hence it is very crucial to understand and the architecture of these event driven systems, and how we can use them, or what are the existing systems. So we will see two of the existing system in today's class. So what are the benefits of having an event driven architecture? The first one is they scale and fail independently. That is, by decoupling your services, they are only aware of the event router and not each other. Hence, this means that your service are interoperable, but if one service has a failure, the rest will keep running. The event router will act as a buffer which is elastic, so elastic that it will accommodate any changes in the workload. The second benefit is you sorry sorry okay second benefit is you develop with agility. That is, you no longer need to write some custom code to poll, filter, and route any events. The event router will automatically filter and push the events to the required consumers, who will then take care of the events. The router will also remove the need for any heavy coordination between the the system which is producing the events and the consumer services. The third one is audit with ease. So an event router will act like a centralized location which will audit your application, and it will create these policies, with which the policies will restrict who can publish and subscribe to this router, control which users and resources have permissions to access your data. You can also encrypt your events both in when they are created or they are at rest. The last benefit is you, with this event driven architectures, you cut the cost. That is, these architectures are push based. That is, you, everything happens on demand as the event presents itself. Okay. This way you are not paying for continuous polling or checking for an event. This means there is less network bandwidth consumption, less CPU utilization, there is less amount of idling that happens, and also less amount of SSL TLS handshakes. So when I'm talking about this event driven architectures, any system that is coming to your mind that you think is based on this event driven architectures, or you've used, or
Ma'am, before that, I do have one question. We are talking about the router. Is this physical router we are talking? It's a software something.
so yeah, so it is at software level.
Okay, it's kind of Kafka or any that's route the traffic.
Yes, so this is a event router, which is, uh, which is its function is to receive events from event producers and intelligently, distribute or route these events to the appropriate, event consumer, which will execute it.
Okay, yeah, I got it now. I can correlate. This is like kind of the Kafka supporters. Kafka is do the similar things. Whatever the data we are generating, that's like an event for Kafka. We'll just push that data to the Kafka, and Kafka decide intelligently which application is going to consume that data. So it's kind of
Yes, yes,
event.
yes, you are right. So Kafka is event driven architecture.
Yes.
So basically, here you will have a event producer, which will be a service or application or system, which will first detect if there is any change, or it will generate an event which needs to execute. Okay, and there will be a consumer, which will be again another service or system, which will listen to these events, receive them from the event broker, and process them and do the required action. Okay, so these are the two main components of the primary actors, you can call them, in the event driven architecture. So, has anyone read about SEDA or heard about it?
No, ma'am.
Okay. So, we will first talk about SEDA, which is an architecture for scalable, well conditioned internet services. So, uh, although SCADA was not the first event-driven architecture, but it is a very, first, one of the first significant and formalized architecture based on event, event-driven architecture system. So the event-driven concepts are quite older. Like they were, introduced in early 1950s or so, but they were formally, SEDA is where they formally proposed a solution for building, a highly concurrent and scalable internet service. Okay, so as you can see in the slide, the internet services before SEDA had many challenges. The first one is massive concurrency. So, even the paper that is mentioned here, the SEDA and Architecture for Scalable Well-Conditioned Internet Services, which was published in 2001 by these authors, you can go through. I had opened it prior, if you noticed before I did a slideshow. You can go through this paper if you are interested to read more about it. So, this paper describes how the systems then, the modern services, were trying to handle thousands to millions of simultaneous requests, and While doing that, these threaded systems which were existent before this event-driven architectures used to break down due to memory consumption, context switching, or lock content. And why they used to break down was because of huge variance in the load. There used to be like sudden surges where flash crowds or some breaking news or some celebrity posts. Like there is a concept of Justin Bieber problem in Instagram, where every time Justin Bieber posts something because he has 56 million followers, it brings the whole service down, slows down because Justin Bieber posts it. So so there are such huge variances in loads that can happen. Then uh, there is dynamic service logic, that is dynamic content and frequent deployment changes happen. And because of that, there is this unpredictability of how the resource will be used. So the authors mention that the existing server designs, which were there then, were brittle and they were not good enough because their resource control mechanisms were not visible to the application. And because of all these characteristics of the internet service which was existed before SEDA, they it motivated them to build a model that could, you know, condition what is the load, stabilize what will be the throughput of the system, and also maintain a predictable performance even when there are, when the workload surges. And that's what exactly the SEDA targets. So the authors found several key problems in the existing server designs. The first one was that the operating systems uh, were obviously hiding the resource information behind the abstractions, like there were threads, sockets, and processes. Applications could not see or reason what is the queue length, what is the CPU contention or backlog buildup. And authors say that applications had no visibility into what are the resource bottlenecks, and they could not make any informed decisions. The second problem was the threads were could not scale because threads were used to before SADA you used to create threads per request, and because you used to create threads per request, there was high memory usage. Because there were multiple threads, there was a lot of context switching. Poor cache locality also was there, and it used to lead to contention. The third problem was, although there was replication of data across multiple nodes, the replication added more consistency overhead, and it did not help to uh, you know uh, have the replicas in across, or you can say prevent the overload because of this different replicas. And due to all these issues, the paper argued that we need a new architecture that will expose the research usage very explicitly, and it will give applications the ability to respond to what is the current load in real time. So there is a concept of saturation point, which is a central concept in this paper, where in threaded services, as the throughput increases with thread counts initially, but after a certain point, the saturation threshold, that is CPU time, is dominated by context switches, cache misses, and synchronization overhead. Okay, so the author demonstrated experimentally that servers beyond this saturation point not only fail to improve the throughput, but the throughput also collapses. And this collapse sometimes happens, suddenly because of this overload of propagations. And this is what the authors wanted to overcome, this saturation point, because of all these reasons, and they claim that SADA's design, which is a staged design, there are multiple stages, where each stage will have its own queue and a concurrency controller. With this design, it will ensure that the overload in one stage will not get cascaded into the entire system. And how do they do that? We'll see in the next slide. So, uh, thread per request designs were simple, but they were flawed because uh, when we say we are using threads, threads are optimized for time sharing. We can get massive throughput using threads, but they also have cons. They have they cause frequent context switches. They also affect the CPU cache, and we do not have a mechanism to regulate the request admissions or any flow control. Hence, although we have thread pools, which could help, which was a traditional solution earlier, but the authors suggest that the thread pools still hide resource contention and they cannot dynamically adjust to changing loads without complex, manual tuning, which is not always possible. So, hence, the authors also stressed that uh, considering we have several high performance events, which are, uh, you know, where uh, we may or may not need a large number of threads, we need event driven systems. And why do we need event driven systems? Because for event driven systems, you will have a very low overhead. You will get high concurrency. You will also have efficient CPU usage. There are some cons as well for event driven systems. They are uh, they are a bit difficult to program. You have little OS and tool support. When the paper was published, now it's not that the case. There is no isolation between parts of the application. Event scheduling is also tightly coupled and it needs the application logic. We also require non-blocking IO support everywhere. And they are, they were slightly difficult to modulate or tune performance. SADA, which was proposed, adopts the efficiency of these event-driven systems, but it also introduces stages which improve the modularity and control of the systems. So, what is this new architecture that we are talking about, which was introduced by the authors? Here, the new architecture expects that you expose what are the performance bottlenecks. You separate event handling from resource control. It has to be easy, to module and easy to program. It should be able to handle overload very gracefully, manage the overload, and sync or grow the architecture accordingly. And it should be able to work with some general purpose operating systems as well. So the solution to all these goals is a staged event driven architecture which will decompose applications into small resource control processing stages. So what are these staged architecture is, as you can see in this figure. So you can uh, imagine or think of SADA as a factory assembly line which will handle requests that are received in a server. So instead of one big team doing everything, the work is broken into stages where each stage will specialize in one part of the job. Between stages, there are queues where work waits its turn, and each stage has a small team of workers or basically threads. They take item from the queue, do their job, and pass the result to the next stage. You also will have a manager, which is a controller, which will keep watching how busy each stage is. And if it finds out that if one stage is overloaded, it will add more threads or more workers there. If a stage is idle or too fast, it will remove some workers because it's not needed. If the queue is getting too long, it will slow down the input or share the load, and all these adjustments will be done automatically. And because of all these adjustments, your system will stay stable even if there is sudden traffic spikes. So basically, what is the core contribution of this paper is, you will have your you will have stages. In each stage there will be a queue, which is a buffer, or you can call it a control point, a thread pool, which is the workers which you will employ. There will be an event handler, a scheduling and resource controller. And with these four important services, that is queue, thread pool, event handler, and scheduling and resource controller, you will be able to get the modularity that you need, which is each stage represents a well-defined unit of work. It will also provide you back pressure and load conditioning, which means that queues enforce boundaries. When a stage overloads, you upstream the stage, and if there is low load, you slow down and drop the unnecessary task. This also provides you independent concurrency because each stage has its own thread pool size, and you get adaptability because controller continuously tunes the concurrency and batching based on what is happening at real time. And these, what are these real time metrics? They are queue length and what is the service time. So we'll see each of them in detail now, starting with what a queue is. So the SADA queue is not just a buffer. It is a control boundary which has multiple rules. The first rule is it takes care of overload management. So if the queue is full, the stage can apply back pressure, it can drop events, or it can, if the queue is empty, it has less number of tasks, it will it will increase, it will not drop the event, it will continue, or it will not degrade the service quality, and it will ensure that the stage is managed gracefully. Then there could, it also, the queues are also responsible for bottleneck detection, because queue length becomes your real-time metric for a system to understand if the system is stressed. So this was not possible with the traditional OS abstractions because queues were not available to us. Here the queue is visible to you, so you know what is the real-time metric, your real-time stress on your system. Also, queues help you to ensure that there is isolation between stages, because any kind of misbehaving, or if there is a slow stage, it will not harm the other components. Okay, and this is one of the you can call this as to be the one of the biggest strengths of your SADA architecture. So how the next one is your thread pool controller. So the thread pool controller is very important because it is the one which dynamically adjusts the concurrency by continuously observing what is the queue length and what is the time it is taking to execute a service. So if the queue length is exceeding the defined predefined threshold, it will increase the threads. If it observes the threads are remaining idle, it will shrink the thread count. So the experimental result, as you can see here, show that dynamic control will stabilize throughput and prevent erratic tail latency. So this, because of this, you are able to, if you see this figure, based on the workload, the thread pool size increases dynamically. And here, as you can see, the other goal of this thread pool controller is to schedule for low response time and also high throughput. So here, as in this case, it is the event handler is observing the queue, then accordingly creating the thread pool, then based on, and provides, then sends the, events to the next queue stage as well. And because continuously checks the rate and schedules the threads accordingly. So now how do you decide what is the batching factor? That is the number of events which are consumed by each thread. Is if you have large batching factor, you will have more locality and high throughput. If you have a small batching factor or less number of events which are consumed by each thread, there will be low response time, which is seen in this graph as well. So the thread pool controller always tries to find what is the smallest batching factor, which will give you stable throughput. And this will ensure that with reduction in batching factor, when the throughput is high, we will have, when throughput is high, it will increase. And when throughput is low, it will decrease. So, with whatever we have seen so far, SCADA, which is a staged event-driven architecture, is a combination of event-driven and multi-thread. It has event queues, which allows inspection of request streams. It can perform filter, aggregate during peak load. There is feedback control, which is taken care of by the controller based on what is the happening in the event queue. It provides the feedback. It also decouples load management from service complexity. And because there are multiple stages, they are meant for modulation and ensure that the stages are happening constantly. So we are able to achieve all the four goals that we wanted to achieve through this new architecture. So then there is Sandstorm, uh, which is used in SCADA for asynchronous socket I/O. So here, what happens is this asynchronous I/O, which is built entirely around, how the SCADA principles happen. This includes, what we are talking about, to give you a context, is it is it is the implementation of SCADA on the actual implementation platform for the SCADA concept, which was introduced by the authors in the paper. Okay, so so this was Sandstorm is the name of the internet service platform that was built to demonstrate and implement how the staged event-driven architecture works. It was developed by the same Matt Welch, who was the author of the SCADA concept. And this was developed in Java, which was using the non-blocking I/O interfaces to ensure that we get high concurrency efficiency. So here in this Sandstorm implementation of SAD architecture, you can see that there are stages. One for accepting new connections, then okay, so accepting new connection, then there is you read from the sockets. Then once you read from the sockets, you write what is the response and you manage the connection lifestyle. So this demonstrate the separation of each of these stages will give you enough modularity and high concurrency, and you will be able to outperform what the traditional server designs were there. So as you can see here, there will be application which will go to the queues based on what needs to be done. It will read, write, or listen, and then stage wise it will perform the required task. So here you can say in this particular graph, SADA asynchronous socket layer, as the number of connection increased, the bandwidth also increased. Whereas the thread-based asynchronous socket layer, which was earlier being used before event-driven architectures, as the throughput or as the number of connections increased, the bandwidth decreased and you could not go beyond 400 connections for this particular experimentation that they did. Whereas the SADA based Sandstorm implementation was pretty consistent and could continue and could be scaled beyond even 4096. So imagine 256, around 256 or 300 compared to around here it is around more than I think 8,000, 10,000. So Haboop is the first full internet service which was implemented using SADA. So the key observations from the experiments of Haboop were that Haboop achieved 10% greater throughput than the Apache and Flash server, which was there. Although Haboop was written in Java, Apache stopped accepting new clients after the process limit was exhausted, like maximum 150 processors Apache could, handle. Flash cannot accept that time it could not accept more than 506 simultaneous connections due to the limits it had. But Haboop continued serving thousands of concurrent clients while maintaining that the behavior to be quite predictable. So this validated that there are architectural benefits of SADA, and it is not just the theoretical performance, but it has enough, enough architectural nuances which makes it a real world solution. So you can see in this figure Apache and Flash, kind of saturated after around here after there was no growth. But with SADA, you could increase the number of clients. So now, so how do you evaluate the systems like all these Apache, Flash, or SADA systems? To do that, you have a matrix which is known as fairness. So since the authors showed that Apache is extremely unfair when there is load, some clients get stuck indefinitely because it is not just able to scale. Flash also displays, poor fairness in terms of how much concurrency it is able to provide. Haboop we expect is showing, or it is able to maintain significantly higher fairness because because of obviously the SEDA stages which ensure and regulate the load at each boundary. And by fairness, what do you mean by fairness is how many, how many number of requests you get and how many clients you have. So because we'll see the formula in the next slide. So because of this, the authors claimed that, you know, this SEDA is, or Hadoop, which is the first implementation, is well conditioned. It's showing well conditioned behavior, which is predictable. It has stable performance, even when there is increase in overload. So the formula for fairness is how many, in terms of number of clients and number of requests for each client. So XI is number of requests for each client and number of client is this gives you the fairness index. So if we measure fairness using the formula, what was seen was that Apache had here this is the throughput. If you see Apache fairness is 0.98, the fairness of Flash and Hadoop was similar. Apache again, as you for 256 clients, Apache was still reasonable. Where and but as you increase the client, the fairness reduced significantly for Apache. Flash was doing still fine. Hadoop, yeah, the fairness was 0.98, which was close to uh, you know both Flash and Hadoop.
Ma'am, what is this RT mean and RT max?
Response time. So as you can see, the response time, although in this case Flash looks like fairness wise it's fine, but the response time wise it's very bad. It's terrible. As you can see, the maximum response time was 37388, whereas the maximum response time in Haboop is 3886.
Yeah.
Similarly, but for 256 clients also, the maximum response time is pretty low compared to the other two. Even the mean, if you see, Haboop is doing much better. Here, RT mean is fine, but the fairness is low and RT max is high. So, in terms of RT max, in both the studies, Haboop is doing much better, and fairness wise also, it is quite stable. As you can see here, the if you compare the response times, Apache might have lower response time in the beginning, but as the system size grows, the response time also increases.
So, ma'am, is there any relation with of a response time with fairness, or how are we calculating the response time here?
Can you please repeat?
Is there any relation between response time and fairness? And second question, is there any formula to calculate this RT mean and response time basically?
So, fairness formula, as you can see, is this, and
Yes.
response time formula uh, is not. So, response time is the time it takes, for It will be basically whatever is the time which you need to wait in the queue, plus whatever time takes to do the execute the process request. That is basically how the fundamentally the, because that's the time take spent waiting and the time spent waiting or executing. So it
How
will be
it's
like once the request is sent, it will start. It will the it will take the waiting time, plus it will waiting time in the queue, plus it will add the time for execution. That's the total response time.
how it's different than the throughput then?
How it is different than
Throughput.
throughput is multiple requests sent and how many are completed per second, or
Okay. Okay. So this is something if I am sending one request and
huh,
this is the main time to get the response back.
yes, yes. So this is the mean time to so let's say you are sending 10 requests, okay? The
Yeah.
one, so one request took 600 cycles, 600 milliseconds, sorry, and the another request took 10,000 milliseconds.
Mm-hmm.
Yes. Give me a minute. Yeah, sorry. Huh?
Yeah.
Huh. Yes. Sorry. Sorry for the interruption. So, uh, yeah. Uh, continuing our discussion. So, let's say you have, uh, we are imagining for 10 requests. Okay. So, one request takes 600 milliseconds, another takes 300 milliseconds, another takes 500 milliseconds. RT mean will be the mean average time taken for all these requests, and RT max will be whichever is the maximum response time in this set of requests that we have received. It will be RT max. Is it clear?
Yes, yes. And this one more question, this Haboop. Is
Yeah.
it kind of Haboop is also a kind of framework like Apache and Flash?
Yes. So Haboop was uh, the first implementation, which was like um, uh, yeah. So it is like Flash and Apache. Yes, but it was based on SEDA.
Yeah. Architecture is different.
Yes, architecture is different.
Okay.
So, any other questions? So, why we are comparing Apache, Flash, and Cedar? Because they are representing three different approaches for designing the concurrent servers. Then, the Apache model was thread per request model, where a new process or a thread was created as soon as you receive a request from your client. Okay. In Flash, the model was a single event loop where thread is to handle hundreds or thousands of connections using a central event loop. Whereas in SEDA or in Haboop, we have staged and queued architecture. And that's why we are comparing all three. And based on that, we observed that with Apache, there were catastrophic failures as there were increase in throughput was happening. With Flash, it is not that bad, but there are issues because of uh, blocking in terms of Flash, where if there is some uh, if there is um, single blocked callback, it will stall the whole server. because it's a single centralized event loop which has with callbacks. SCADA showed that it is very graceful in terms of how how the overload is handled because of queues and using dynamic controllers which were managing the workload as and when the requests were received. And that's what these results are also showing, that the response time, mean response time and the maximum response time is pretty fair for Abu with if we compare what with the Apache and Flash. So yes, moving on. Sorry.
Ma'am, I had a couple of questions on earlier slides,
Yes.
much earlier slides. I picked them much earlier. Can we take them?
I think,
There, there was a mention of increase in threads resulting into more cache misses. How? Yeah, this is the slide. So here we say
okay.
cons. As part of cons, we say with number of threads getting increased, we will have more cache misses. So how does those two things correlate? Is the question.
Okay. So uh if you have a lot of threads which are spawned, that what happens is many threads will try to read from memory, and for every time you are trying to this is the concept of basically cache contention. I think we
Mm.
discussed it somewhere.
Oh
Yeah.
yeah. Okay. Okay.
Yes.
That's cache
So
contention.
yes. So it could happen, both cache contention and cache coherence can happen because of increase in thread size. So each active thread will try to ask for some amount of data and instructions, and you will try to put that in cache. But when multiple such working sets of threads are happening which are trying to run concurrently, the total size of cache may not be sufficient to store the request that each thread has, and might just get replaced. So the data might
Right.
get evicted, and it will, whenever it is needed shortly again, there will be no, it will not be in the cache, and it will result to cache miss.
Okay. Got you.
Okay.
Got you.
Yeah.
Yeah. And there was some mention of FSM on the subsequent slide. Can you just move on further with the slides? Yeah, FSM, sorry.
Yes.
What does FSM stand for?
Yes. Here we are talking about FSM, where we are saying um, yes, so there was no isolation between FSMs. So um, when okay, so FSMs were uh, like the software where the pattern you can call it, which was managing if when there is any when it was trying to manage some events. Okay,
Mm-hmm.
FSM has to determine what action needs to be taken based on the incoming event and what is its current state. Okay, so in event driven systems, what we try to do is, as FSM will try to ensure that events are for a single entity, that is whatever specific user session is there, or is there, if there is any network connection, and it tries to process this sequentially. It also ensures that you define all possible states or components for each of these event. Okay,
Mm-hmm.
that is whether the event is idle, whether it's connecting, it's connected, closed. Basically the same finite state machine of how
And state
what will
machine.
happen inside a event handler. Okay, so it will have this FSM will have states which will be what is the finite state of what will be possible internal modes that will happen, then how it will take the external stimuli which will trigger a change in the state, then how these transitions will happen inside. I hope you all remember the compiler FSM. Are you able to connect the finite state machines? So
Not really, at least.
okay, finite state machines were are like let me so you had one input stage,
Mm-hmm.
and if you had, let's say, received 0, you would go to one stage. If you received 1, you would go to another stage, and so on. There was fixed set of rules based on
Okay.
which the transition used to happen.
Okay.
So how FSM works the same way. That is, it waits in the current state. When an event arrives, usually from the queue or event loop, it will check what is the transition rule based on the current state and based on what is the event type. Then
Mm-hmm.
it will execute the associated, whatever the action that needs to be done, like maybe sending a message, saving the data, or based on whatever the event is. And it will move to the next state.
Okay.
Yeah.
Okay.
And
Okay. Get it.
that's how it
Mm.
works.
Okay. Thanks.
Okay. So, yeah. So, I think we covered this. And yeah. Okay. So, there is another concept which is DQ principle, which is which was by Eric A. Brewer, where uh, D into Q, that is D is data per request and Q is queries per second, is equal to constant. So SEDA tries to enforce this principle by ensuring that there is, the concurrency gets reduced based on data per request, because data per request and queries per second have to be constant. It increases the batch size, that is, adds more threads. It will apply break pressure, as in if it is getting, if the workload is increasing, it will take care of that. If there is, too much increase in the events, it will evaluate and it will drop the events when needed. And because of this, because it enforces this principle that you whatever data you receive per second and the queries that you receive per second have to be constant. It ensures, because of this, it gracefully takes care of the overload instead of crashing, because it follows this principle very strictly. So I hope you all understood what it is.
No, ma'am. Can you?
Okay, so yes, so
Yeah.
DQ
And can you
principle.
please,
Yeah,
yeah, can you
DQ
please explain
principle.
QC, Q0, DVDF as well?
Yeah. So, okay. So DQ principle is basically a design guideline which is used for these giant scale internet services. So basically, it is trying to relate the system capacity to whatever the movement of data it receives. Okay. So the principle says that data per query into queries per second have to be constant. That is, it adds a limit of what is the system's capacity, which means the total data movement per second has to be bounded by what is the physical bottleneck and whatever whatever that it has received. So the total data movement is ultimately limited by what is the system's hardware resource. And if you follow the DQ principle, it ensures that you get a constant, sustained, maximum throughput. So in practice, what happens is if a giant scale service is there, it increases the complexity or size of the data it returns for each data query, its maximum throughput must decrease to keep the overall data movement rate within the system, uh, to ensure that the physical limits are taken care of. So by DQ principle, the strategy is you reduce the data per query. When the system is overloaded, a designer can choose to reduce the amount of data returned for a query. By reducing the data returned per query, the system can maintain a high throughput and yield, provide a better yield. Alternatively, if if you have to reduce the queries per second, designer can implement admission control, which will ensure that you queue the incoming request, and because of that you maintain the quality and of the data that you are returning at the cost of overall throughput, that is queue. So if based on, like here in this case, in this particular figure, so server capacity has to be that whatever it receives into whatever data it has, data per second that it can provide, and the request have to be constant. So if this queue, in this particular example, the total yield, the queue will be the total request that you receive divided by how many you are trying to, you know, uh, process at a time. So similarly, the how much data you are trying to provide per access becomes your, you know, harvest, which is what you are, providing or what is being requested. Okay, total request over what you are providing is the yield and the harvest. Is it clear now, or like?
Ma'am, does that mean, sorry, just one
Yeah, yeah.
clarification. Does that mean Q0 is number of queries which are received and QC is actual queries which are being served by system?
Yes. So yield will measure if the how system is able to complete the request, because it is being calculated as queries completed over queries offered.
Okay, C and O. Okay. Queries
Yes.
completed, queries offered.
Yes.
Okay,
And
okay.
harvest is data available in response over total complete data.
Okay, so that does mean QC, the number of queries which are being kind of processed are
Mhm.
corresponding to DV. If you see the lines are in
Yeah,
same
yeah,
color,
yeah,
right?
yeah,
Green
yeah.
color.
Mhm.
So QC corresponds to DV and Q0 correspond to DF. That does mean DV is the data which is required for QC requests.
Yes,
Output data corresponding to those
yes,
queries. That is
yes,
what I mean.
yes.
And then DF is the total data which will actually be required for all the requests which are there in the input,
Yeah.
which are not served that way.
Mhm.
Okay,
So
okay.
when a system receives like gets overloaded, and you
Mm-hmm.
know it has to, we have to ensure that the system is stable. So you reduce the amount of data that you are trying to provide. Okay.
Uh-huh.
So
Uh-huh.
it's basically dynamic data reduction, or you can call it shredding the load
Huh.
to ensure that you preserve the rate of successful responses, that is Q.
Okay, what would happen to requests which are Q0 minus QC? Those will not be served. Is that what you mean?
So uh, they will be served, but they will have to be, they'll be in the queue, right?
Okay,
So
they will be
they will
queued up.
take a bit longer.
Okay, I see you now. Okay, okay, okay. So QC is going to decide how many queries which are going to be processed by system actively.
Hmm.
Q0 minus QC is the count of requests which will remain in the queue for their turn.
Yes,
And
yes,
correspondingly, DV is going to be the data which is corresponding to QC.
yes,
And DF is the total data which will be returned once Q0 queries are kind of served.
yeah.
Okay, that helps. Thanks.
So, uh, so in the retrospective, which is a blog by Matt Welch, the same author, uh, he identified like few things that SEDA got right and wrong. So he said what it got right was the explicit exposure of resource bottlenecks using queues, the modularity it gave via stages, the load regulation it could do using control theory, and also uh, it led to many new future systems which were like Kafka, Storm, Akka. But there were a few limitations because it was based on Linux threads. They were a bit immature in 2001. They were like later a lot of changes happened. Then there were no non-blocking IOs, which was difficult and inconsistent. There were again too many parameters to tune manually. Also, with with uh, because it had stage per queue per thread pool, it 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 could be that it could also say that you know um it was a bit of overkill sometimes because you had queues every stage, and every thread pool. But overall, the SEDA model still remains a foundational concept in the scalable distributed systems. And uh, it is important to understand that SEDA is more than just a server architecture because it represents the philosophy of designing a scalable system. We can think of SEDA as a combination of four major ideas. The first one being feedback controller, which was automatically tuning and it was automatically ensuring concurrency and doing the batching based on the load. The second was idea was stage modulation, where the application was broken into multiple stages and there were clear boundaries for each stage. Then event or message driven flow, where events move through the stages like a pipeline. There were explicit application metrics such as queue length, the processing time. So, because with these metrics, the system could adjust itself. So, this idea of explicit data driven control over concurrency has influenced many modern, platforms. So, as one of you mentioned, Kafka. So, the Akka model, which is actor model with message driving stages, then Kafka, which is a distributed message queues and back pressure, Storm, which is also a known model, and there are steaming engines where even the data flow engines like MapReduce, uh, they Spark also use pipeline stages and they have operators and back pressure. So although SCADA itself is not still like it was not um, uh, widely deployed as a Kafka and all, but it is uh, a concept which has the needed what you can say needed concepts which could make a modern distributed system design scalable. So if we combine SCADA stage control with large scale cluster designs and use load balancer, we get the system which is very elastic, you can call elastic in terms of how it handles the loads. So this is what uh, the a cloud native architecture needs today. And we can also say that idea of using the feedback such as control loops based on the metrics like queue length is has become an industry standard now. Many companies like Facebook, Tencent, Alibaba, Baidu have publicly described using forms of PID controllers which have like similar feedback systems which dynamically tune the resources as and when they receive the request. So the takeaway that we have from our discussion on SEDA today is SEDA introduced the idea that throughput, concurrency, and performance should cannot be hard coded, right? Because you have to continuously measure and control using the feedback loops, and this idea has become a foundation for many modern event-driven serverless systems, which so which are in use today. So we can adapt the discussion on SEDA with by exploring the three major server design paradigms that we have learned here, where the we had multi-threaded servers which rely on thread per request on thread pools. They were easy to program. Uh, then event-driven architecture, which are extremely efficient but slightly difficult to program because the application logic can be a bit tangled and event loops are there. So then staged event driven architecture, which is SEDA, which is the model that tries to combine the best of both the worlds, that is multi-threaded and the event driven architecture, where it breaks the system into stages connected by the queues, each stage independently controlled using the feedback mechanism, and it provides you the modularity that you need, the feasibility into performance, and also helps you to gracefully take care of the overload. So in this, we learned a few concepts such as saturation point, which is the point at which adding more thread stops increasing the throughput and starts hurting the performance of your system. Then we also talked about Jain's Fairness Index, which is a way to measure how evenly a system treats all clients under load. The DQ principle, which we discussed in detail, where we said that when load increases, the system should not collapse, but they should reduce the performance in a controlled, predictable manner. So we can say the important lessons that we learned was modulation, that is breaking the computation into stages. This does not make the system easier to program, but it gives flexibility because each stage can be scaled, monitored, and controlled independently. There will always be a trade off between transparency and performance because traditional operating systems used to hide their queue, scheduling, and resource contention behind whatever abstraction they provided us. But SCADA shows that exposing these details and controlling them explicitly helps to better scale and you can have more predictable behavior. So the big takeaway from SCADA could be that better visibility and modularity helps you to gain better performance. And when you expose the right important metrics and have a feedback control, feedback based control, the system will scale, and it will scale pretty gracefully. So if I missed any other point regarding SEDA, you can tell me. Maybe we can take a 5 minutes break and then we talk about a fast architecture, which
Yeah, ma'am,
is
one question on one of the slide which talked about Java. Just go back one slide more.
yes.
Yeah, just hold here. What SEDA got right using Java instead of C. Now, there is a specific decision that SEDA is going to be implemented using Java. Looks like. Why the decision
Yes.
was taken? Any idea about that, or why it was Java influenced? Java was chosen over C because C, if we, as we all know, C is pretty faster as against Java, right? So why
Yes.
Java was chosen instead of C is the question.
Yes. So uh, SEDA, I think, basically used Java's library, which was java.util.concurrent, which provides high level of concurrency. It already had blocking queues, thread pool executor, and dynamic thread pool management, which these are like Java's built-in libraries which helped uh, you know build the SEDA architecture better. So uh, if yes, implementing SCADA in C would deliver lower latency, and we might have seen higher throughput because it would have avoided the JVM overhead, which is a major issue in Java, right? The the compilation and the garbage collection in Java. But with SCADA, uh, they eventually found that they had higher throughput over C-based web servers. That was that they observed. So with
Okay,
SEDA, although they sacrificed a small amount of raw speed, they got better robustness. With Java, I would say.
okay, and then implementation simplicity as well because Java provides
Yeah.
concurrency based stuff
Yes.
OOTP,
Yes.
so
Because you use
you
the
don't have to
concurrency.
build it your own
Yeah.
on your own
Yes.
kind of thing. Okay,
Yes. Yes.
okay, I see. Thanks.
Okay. So let us take a 5 minutes break and join maybe 9:30 and talk about fast architecture so that we have yeah, we can learn the new
Yeah,
concept without much overlap. Yeah.
okay, thanks.
Thank you. Okay, so let us continue our discussion, and we will briefly learn about another architecture, which is you know uh, which has its roots in event-driven architecture, or which is event-driven architecture, but is used a lot currently. So we're talking about a fast architecture. Even though SEDA was designed in the early 2000s, and fast has emerged almost a decade later, they have the same foundational ideas. That is, fast is essentially the cloud scale evolution of the concept that SEDA created. And how the two are similar is, the fast is a serverless execution model where cloud platforms run their code only when an event occurs. Have you used any fast model? Anyone? I'm pretty sure some of you must have. No one here has used AWS Lambda.
Yes, ma'am. It's a
Or
serverless compute.
yes, yes. So it is based on fast. Or Google Cloud Functions or Azure Functions. Anyone? So how it works? You you mentioned serverless. Yeah, serverless. So how it works?
Uh, in this case, we just need to write our logic and functions and assign to the uh, cloud, and cloud will like handle the servers, run your applications. You will not get any access of servers. We can just modify your application and deploy it. Where it's going to deploy and what server is configuration, all these things is handled by the service provider.
Yes, yes. So basically, you write a function, you register that function, cloud will trigger it, and then the event will happen. That is, either it will be some file upload, some queue message, a call, right? No
Yes.
servers, no threads, no scaling logic. The cloud will handle everything, right? So
Yes.
basically, the purpose of it is we scale automatically from zero to any number of thousands of invocations, and that is taken care of by the cloud. And any other advantage you see of such a system?
Auto scaling. Yes.
Yes, auto scaling and any
Event
monetary benefits?
event correct. Event driven kind of like we can say
Yes.
event based invocations. Yeah.
And you pay for only for the whatever the actual
What
runtime is, right?
yeah,
So that is
whatever
another
you
advantage, very important advantage. So we can uh we can look at fast as a team of helpers which are trying which only come when we need them and do whatever tasks they need to do, and then they disappear. So we don't keep any servers running, we don't manage any threads, we don't worry about the scaling. We just write small functions, and then cloud runs them, and automatically whenever an event happens, it takes care of it. So in these distributed systems, in the specifically like fast, there are two ways a client can interact with a service. The first is direct API call, where a client explicitly sends a request to a server. If in synchronous calls, the client will block and wait for the response. If it is a asynchronous polling, the client will send a request and periodically check if the it will periodically check or poll what the status, that is, whether the result is ready or not. So in this model, the client will keep asking if the result is ready or not in asynchronous API call. Another method is using webhook or callback registration, where client registers a callback URL or a function or an event handler with the server. The server will store this callback and push the results to the client when the event occurs. So this difference, that is pull versus push, is a foundation for all these modern event driven architectures. So when do you use it and why? So fast systems like AWS Lambda or any GCP cloud functions use these models when specifically direct call models when you want to invoke a function via HTTP or API gateway. You use the callback or push model when the cloud automatically trigger your functions or an event. So the callback and push model is more dominant in fast because fast is mostly inherently event driven. So in fast systems like the AWS Lambda, it is functions which run and you get the response to these events. So these events may come from file uploads, any queue message, any HTTP trigger, some database update, or any custom application events. And this is what basically the webhook or callback model does. That is, instead of client calling the function repeatedly, the platform will trigger the function when the event happens. So fast is basically a generalized cloud scale version of the callbacks where you don't keep servers running or poll anything. You just register function and the cloud will call, when it's ready to execute. That is, it executes the code in response to some event. So direct API calls are simple and intuitive. However, they face scalability problems. That is, synchronous blocking will waste some resources. If there is asynchronous polling, it will generate extra traffic and it will generate, lead to delays. Clients will remain online. They will have to maintain the state, handle any retries. If there are traffic spikes, the server will get overloaded because there are simultaneous API requests. Therefore, direct API requests are not ideal for specifically for highly distributed event-driven systems. That's where the webhooks or callbacks come in picture. They are extremely efficient for distributed systems. The client does not waste time in polling. The server invokes the callback only when it is necessary. They integrate with queues, streams, and event buses. But they also introduce a few distributed system challenges, such as events may arrive late, they may arrive out of order, or might get duplicated. So the client must be prepared for any retries. Also, another limitation is, there could be some network failures also in case of callbacks. So how callbacks are used in the modern FAS systems? So FAS system is, as we discussed, it's a cloud scale managed callback system where a developer writes a function and registers it with an event source. Then this registered event source will be given to a server's runtime manager, which will execute, scale, across different thousands of invocations. It will keep retrying. If there is failure, it will maintain ordering guarantees wherever it is possible, and hence the callbacks become like a structured, standardized, and managed way to use the serverless fast system. So when callbacks scale to millions of invocations, several distributed system issues also arise, such as timing, that is, events may be delayed, retried, or queued. There could be some cold starts because of additional latency. So platforms like AWS will use auto scaling and warm pools to reduce this. The another you know key issue could be ordering. So cloud platforms often provide best effort for ordering, but some systems such as AWS Kinesis will guarantee that you do a different kind of ordering, not a global ordering. Then there could be timeouts. That is, uh, as some of you have used, Lambda functions have execution time limits. So if there are any slow backends or large tasks, they may require breaking this work into smaller events and all that, which will lead to network delays. Another challenge is duplicate events. That is, most fast triggers will at least have one delivery semantics where each function must be uh, there, and it will have some independent logic. That is, if there is a corrupt state, you repeat the execution of the event or duplicate the event. So how cloud platforms solve the fast challenges that we just saw? So they have queues and message buses which absorb if there are any burst, or they ensure reliable delivery. They also have, if there are any failed events, they are retried, they are or they are stored for later inspection. Then independent idempotency is used, is taken care by duplication of your logs. Then you have state machines which have a strict workflow to ensure that fast is taken care of. Then you do partitioning where you order the events or create order of events within an event, so that uh, for each event there is a certain order in which it executes. And it also has back pressure, which is when there is downstream services are slow, queues buffer the load instead of crashing the system. And do not crash the system, but just let all the requests wait in the queues. So together with all these mechanisms, the fast is able to provide the required scalability and behavior that we need from the fast systems. So, uh, so here through fast, we were trying to basically discuss about what are the two types of calls, that is direct API call or the webhooks or callbacks. So direct API calls are used to pull based models, and they require polling, and they need tight coupling of the client and the server's availability. Webhooks or callbacks reverse the responsibility, that is, the server pushes the results. This push based execution is the core principle behind the fast system. The fast platforms basically generalize the callbacks into fully managed, scalable, event driven execution environments. However, there are issues that because of distributed callbacks, introduces a lot of issues such as timing, ordering, timeouts. But cloud platforms also addresses these issues by using managed event queues, partition ordered systems. It also retries and ensures that if any function call fails, it keeps trying. Then there are it uses state machines, and basically this is because of all these different implementations of how we solve the issue. The fast system is a very reliable and fundamental architectural foundation that we have for the modern serverless systems. So, uh, you know, where so basically how the fast system works is we design a function which is small or focused on some specific task. Then we, you know, have state management in fast, which is they don't retain any data between these invocations. So they use appropriate mechanisms for ensuring that each state handles the required request and it synchronizes. It also takes care of cold start, which is minimizing the latency of start, that is the delay when a function is invoked for the first time or after a period of activity. We also, as we discussed in the initial slides, we optimize cost using fast. That is, we because we are using these different practices of using event-driven systems, we are able with fast we are able to optimize the cost as well. So the so in summary, the fast systems consist of of few components such as the function, which will which is like the fundamental unit of fast architecture, where a function is a small piece of code that will perform a specific task or it will respond to some event. These functions in fast are stateless. They do not retain any information between the invocations. Then you will have a fast provider, which will is the cloud service provider that offers this fast platform. We have discussed AWS Lambda, Azure Functions, Google Cloud Functions, or even IBM Cloud Functions. All these providers are responsible for managing the underlying architecture or infrastructure, and they take care of the scaling functions and handle operation tasks. Then there are event sources, where event sources will trigger the execution of functions. These sources can be HTTP request, database changes, any file uploads, message queues. So fast platforms support various event sources, which then leads to the event-driven architecture that we talked about in SEDA. So each function will run its own isolated and execution environment, which will include the whatever the runtime environment dependency it has. And this execution environment is provided by the fast provider when the function is invoked. And once the function execution is over, it is discarded so that you conserve the resources and you are able to handle more resources. Fast scales by dynamically adjusting the number of function instances based on what is the workload demand. So you can scale horizontally, that is you can add more instances, or you can scale vertically where you can add more resources to each instance. Then these functions are invoked after synchronously or asynchronously based on what is the nature of what is the nature of the event. So synchronous invocations will happen when we are having requests such as HTTP request, and asynchronous happens when a response is not immediately required, such as we are trying to process something from the queues. Also, the fast provides you monitoring and logging capabilities with which you can track the performance, the execution, and errors of each function. Developers can monitor metrics such as execution time, uh, invocation count, what is the error rate, and also view all the logs so that it can troubleshoot and optimize for better performance. So, anyone wants to add more to the to what we discussed about fast or the challenges? So real world examples of fast could be even the Netflix uses obviously AWS Lambda. Airbnb also uses AWS Lambda. Slack uses AWS Lambda.
Ma'am, there is one more class next week or
Yeah, that is a revision class. So,
okay.
uh, yeah, I was thinking you all can maybe send me in chat by Thursday or so which part of the course you want me to revise or any specific examples you want me to discuss. I think that will help me to plan the class better.
Yeah, sure, ma'am. Maybe I think you can just cover or brief us about all the important topics and more focused topics so that we can just go over once.
Yeah, maybe I will try to discuss some similar examples that I'll expect from the in the exam too. A few.
Yes.
Yeah. On this course, as I mentioned in the beginning, on this module specifically, the questions will be more theoretical. Uh,
Yes.
yeah. And I'll upload the slides right away so that you can prepare your slide deck for the exams. Print and keep it ready.
Are you going to merge all the slides and send us one slides PDF something?
If you want, I'll do that.
We got it from other subject, one document for all the slides.
Okay, then I'll create and share whatever I've
Yeah.
done so far. Yes. Okay, in that case, we
Ma'am,
can,
how should
yeah.
we revise when it comes to open book tests? How should we revise things?
So, um, you um with open book, closed book, actually revision will almost remain similar.
Okay.
Yeah, you can maybe think about more what could be the applicative questions in the particular module, what possibly could be asked.
Okay. And ma'am, can we take sample questions next in the revision lecture so we can try to figure out that part?
Sure, sure. I will do that.
Okay.
I will discuss
Okay.
about some questions in the next class.
Ma'am, what kind of difference we can see in mid-sem and end-sem, as in open book and closed book? What kind of difference would be there in questions?
Mhm.
What sort of
Um,
difference we can expect?
so I don't think it will be a lot of difference because I'm not sure. As far as I know, the first mid-sem exam was tough to a few people, many people. So the type of questions will be similar. Only thing it will be open book this time because increasing the complexity of the question, I'm not very sure how comfortable everyone will be.
Okay, that will help. Yeah.
Yeah.
Like most of us would be giving open book kind of an exam for the first time, as in
Oh, okay.
it's for the first time for me as well. So I'm not too sure
Uh-huh.
on how the questions are
So
laid out.
yeah, usually when we have open book questions, at least on campus, uh, for on-campus students, the all the questions have to be applicative and um, they have to be in such a way that uh, having the book only having the book will not be enough for answering the questions. You have to have prior understanding and thorough understanding about the concept so that you are able to answer. Just going through the notes would not help you on the day of exam. So that's how the questions are usually defined. They are more applicative questions.
Okay, and how would the book help in that particular situation then? If you prior know it, then probably you'll be able to answer that without the book as well, right?
Yeah, sometimes now with book, it's like you are not forced to memorize everything,
Mm-hmm.
and you can um, focus on more understanding the concept over memorizing it.
Okay, okay,
So whatever you need is available to you in the slides or whatever printed material you have, and you can focus on understanding the course.
okay. So concept-wise, how to apply it is something which will be explored in open
Hmm.
book,
Yes.
is what you're trying to comment. Okay.
Yeah.
And as
Yeah.
as far as preparation standpoint is concerned, how would you suggest us? As in, how should we or what difference we should have as against the preparation which we did for midsem?
So would suggest you now with respect to OpenMP, CUDA, try to you know write at least one or two problem first two problem statements. Try to write the code, understand how things work. Okay, then um for fast and today's event-driven architecture, you will have and Hadoop. You understand how the architecture is, what are different parts, how are they, what is the what is the importance of each part, how are they connected, and why we have them for in this architecture. So the differences. So more of theoretical questions.
Okay.
So, ma'am,
Okay.
mostly we are going to get the theoretical questions this time.
Not mostly. A few theory and few
Okay.
problems.
Okay.
Yeah.
Right, the last exam was like four programs, full stop. There were
Yes.
no theoretical questions, nothing of that sort, and it was comprehensive in real sense, as in MPI, OpenMP, CUDA. All languages
Okay.
had a respective problem. 10 marks
Kuda
each.
Kuda was not there, I think.
CUDA was not there. Okay.
Kuda was not there.
Yeah.
OpenMP, MPI, and pthread.
Yeah, pthread.
Pthread.
Hmm. So see, I have to also think about the your evaluator, because she has to go through everyone's questions and evaluate as well. So accordingly, it we have to also have consider that and design the questions accordingly, and at the same time cover all the concepts. But I got the understanding that it was tough for many people. So this time I've kept theory questions on purpose, although it's
Yep.
open book. So because the important part of learning a course is not grading or the scores that you get, but it's about learning the concepts and
Yep.
getting the knowledge out from this whole uh, 4 months of discussions and or whatever we have had. So yeah, so I do not want to insist a lot on making it competitive. I want you all to feel that you've learned something through this course and you could apply that knowledge.
Yep.
So it's pretty late. So thank you for joining. Sorry for the last minute change in schedule, and all the best for your competitive preparation. And we will meet in the next class and revise a few practice questions and discuss what you should be prepared, how you should prepare.
Thank you.
Okay. So
Thank you, ma'am.
so new topic wise, this was the last session.
Yeah,
Is
yeah,
what
yeah.
you-
And
Okay.
no more topics.
No more.
Yes,
Okay.
yes.
All right. Try and get that PDF file as early as possible, ma'am. The way you said.
Sure.
Yeah, we need to
Uh,
we need to take a printout of that.
Sure, I'll make one today and share because now the slides are ready. Yeah,
sure. That
yes,
will
Okay.
help.
I'll share.
Thank you.
Thank
Thank
you.
Thank
you.
you. Have a good night. Bye.
Thank you, ma'am.
Thank you.
Bye.
Thanks. Bye.